Hello, everybody. How are we doing today? Can you hear me okay? Everything A-okay? How's life? How's quarantine land? Etc., etc. All right. So, hello and welcome to Open Q&A for Physics 1. My name is Kelley. I am one of your Physics 1 streamers. The other one being Peter, who does the 1 o'clock streams. And yeah, so today we are here for you. If you have any questions, concerns, any topics you want to cover, put them in the chat. Yeah. If nobody comes forth with questions, then we're going to go into some prepared stuff, namely collisions and rotating stuff. A work one? Sure. Let's do a work one. Let me go find a work one. Okay. Da-na-na-na-na-na. That was one that I did not prep for because I was like, oh, nobody ever asks about work. And then you go and ask about work. Just kidding, just kidding. Okay, let's see what we can find. That's a conservation of energy one. That's a waves one. Nope. Let's try this one. That's box on pulleys. That's circuits. That is a spring. Okay. Not nothing. Do 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 do. We might be out of luck. That would be terrible. Circuits and waves. I don't see any work ones. Alright, is there anything in particular you want to focus on with work? In case I can't find an actual free response question with work, because that's what it's looking like. Do 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 do. Oop. And alas, my friends, there are no using work energy instead of forces. Okay. Okay, we can do work energy. We can do a conservation of energy problem. Unless... Okay, I think the closest that we're going to get to work energy problem without spending a ridiculous amount of time searching for one, because that is one that I did not think to get. It's going to be here we go. This one. Not that one. Where the heck did you go? Okay. It's going to be this one. Let's zoom. Okay. And pardon my up close face really fast. Go play. Okay. So this problem is from the 2015 free response questions. It is the closest thing to a work energy theorem problem that I could find. So here we go. All right, so we have a block initially at position x equals 0 and in contact with an uncompressed spring of negligible mass. And the block is pushed back along a frictionless surface from position x equals 0 to x equals minus d, as shown above, compressing the spring by an amount delta x equals d. The block is then released. At x equals 0, the block enters a rough part of the track and eventually comes to rest at position x equals 3d. The coefficient of magnetic friction between the block and the rough track is mu. On the axes below, sketch and label graphs of the following two quantities as a function of the position of the block between x equals minus d and x equals 3d. Now, you do not need to calculate values for the vertical axis, but the same vertical scale should be used for both quantities. And we have the kinetic energy and the potential energy. Okay. So, first thing we want to do, let's go open up our nice, beautiful graphs. What do y'all think the kinetic energy and the potential energy is going to look like? Just like in words. Do you have any ideas? Okay. So when is, starts out with the P's, okay. So when we smush it all the way to minus D, we know that we're going to have a maximum of our potential energy, right? So let me open up a whiteboard. And then where is our kinetic energy going to have maxima and minima? That's 0. Cool. Okay. So let's open this whiteboard up. Okay. Let me switch over to the whiteboard. Sorry, there's not a better way to do this without zooming in on my face. Okay. Blank. Focus. Right. Okay. So we have our beautiful graphs. This is going to be a hideous graph. I apologize in advance. So we have minus d, 0, d, 2d, and 3d. Okay. So we said that our potential energy is going to be at a maximum when we're smushed all the way towards the end. So when we're smushed all the way at our spring here at minus d. So this is going to be our potential energy U. And our potential energy of a spring goes like 1/2 kx squared, right? So it's that nice parabolic shape with distance. So at equilibrium, so we can draw a nice attempt at a parabola. Blam! On the way down. Right? And then at that point, when it gets to equilibrium, now the block is not actually attached to the spring. That's something that you kind of have to get out of the question, which is not super obvious. So a block is not actually attached to the spring. It is put in front of the spring and then smushed over and then let go, and then the spring kind of launches it forward. So once that spring gets back to equilibrium, it's no longer in contact with the block, so that potential energy goes to 0. Meanwhile, that means once we lose contact with our spring, all of that potential energy is going to be at a maximum for our kinetic energy. Blank, blank. So at equilibrium, that's when our kinetic energy is a max. And if we're losing potential energy like a parabola, that means that we are gaining potential energy like an upside down parabola. Cool. So then once we get onto the frictiony surface, what is our energy gonna look like? Potential and kinetic energy. Well, our potential energy we said was going to be 0 because it's not touching the spring anymore. But what about our kinetic energy? What's going to happen once we get onto that rough track? Yeah, exactly. It'd be decreasing at a constant rate. So decreasing, wow, that's a horrible straight line. I'm so sorry. Until we get to our stopping point. And when we stop, our velocity is 0. So our kinetic energy is also 0. Work done by friction decreases the kinetic energy. Exactly. So, are there any questions about the graph part? Okay, so scoring for this part, as long as you have a reasonably correct shape, like the parabolic shape, you got points. And as long as your total energy is constant in your graph, from minus d to 0, you get points. And then this is something that sometimes gets overlooked. Oh, this is from 2015, the year. Question number 3. So something that gets overlooked when you're doing the graph problems is that like once it gets to 0, you kind of just forget to draw a straight line at 0 for the rest of the graph. Don't forget to do that because that's points. I know I personally do that. It's terrible. Cool. And then also you get your kinetic energy as a linear function because your friction depends on how far you go. Or your work lost from friction, excuse me. Energy lost from friction. Wow, I can't talk today. Okay. Alrighty. So part B, let's swoop back over. Oh, I wish there was a better way to do this. That would be really great. Okay. All right, so the spring is now compressed twice as much to delta x equals 2d. The student is asked to predict whether the final position of the block will be twice as far at x equals 6d. And the student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring, so it will slide farther along the track before stopping at position x equals 60. Which of the aspects of the student's reasoning is, if any, are correct, and why? And what part of the reasoning is incorrect, and why? What do y'all think? All right, let's break this down. So the student says that the spring will be compressed twice as much as before, so the block is going to have more energy when it leaves the spring. True or false? True, right? You're squishing it more, you're putting more potential energy in to the spring, so when it releases, you're going to get more energy when it leaves the spring. Okay? Because it starts with more energy, it's going to slide further along the track. Right? True? False? Why true again? Okay. So if you're compressing your spring more, you're putting more potential energy into that spring. So as you're smushing it up, it's storing more and more and more energy. So when you eventually release that spring, it's going to transfer more energy into the block. So that block is going to start with more kinetic energy once it hits the rough patch because it got all that energy from the spring. Does that make sense? Cool. Okay. So what part of this statement is incorrect about their assumption? It won't go twice as far, right? Why not? Because it depends on x squared, exactly, not x. Cool. Good job. Okay. So that takes us to part C. So using our quantitative reasoning, including equations as needed, to develop an expression for the new final position of the block. Express your answer in terms of t. All right. So let's switch back over to the whiteboard. Excuse me. And then we're gonna focus again. And then we're gonna make a new one. Okay. All right. So what do we got? We know that when we smush our block all the way over to 2D, so our potential energy of our spring goes like 1/2 K, we'll say delta x squared, right? So the energy that we start with, we're taking our block and we're smushing it to 2d distance away. So if I simplify that, I get 1/2 k. 2 squared is 4 times d squared. This 2 and this 4 simplifies to a 2. So 2k d squared. Okay? So then I also know, oh yeah, this is kind of a little bit of a work energy theorem plan, that the work done to stop this guy is going to be the force times however far it goes, force times distance, where my force is the force from friction, which is mu times the normal force, right? But since we're on a nice flat surface with our block, we know it depends on x squared because of the equation. Yep. So the potential energy that's stored in a spring goes like 1/2 kx squared. So it's a quadratic with respect to position. If it was something like 1/2 kx, then if you double the distance, you would double the shot, if you will. Okay. All right. So work done, which will tell us how far we go, is mu mg delta x. Cool, cool. All right. But alas, I do not know how far it goes. That's what we're trying to figure out, right? But I do know that my potential energy gets turned into kinetic energy, and then all of that kinetic energy gets taken away because of friction. So I can set those two things equal to each other. So I can say that 2k d squared is equal to mu mg delta x, right? So if I solve for delta x, I get 2k d squared over mu mg. But alas, I don't want any of the rest of that stuff in there. So let's take the information that we have from the first part. Whoa, sorry, that's not what I meant to do. Okay, so we're gonna leave this here. Dun, 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 dun. All right, so this was U, we'll say 2 from far away. Maybe. Okay. Okay, so then from the first part, we know 1/2 k. I smushed it by d, ends up going to mu mg, and my distance was 3d in that case, right? So one of my d's cancels out. So I have 1/2 k d is equal to mu mg times 3. Okay, so now all I'm trying to do is just get rid of the k's and the mu's and the m's and the g's by using the information that we have from the beginning. So this was the first part of the block, this was the second situation. All right, so if I rearrange this, I get mu mg over k. Yeah, we'll move the k over there. Is equal to 1/2 d divided by 3 d over 6. Okay. So here, where I accidentally erased it, my delta x was 2k d squared over mu mg. So the reason I did this, so we know that mu mg over k, mu mg over k is equal to d over 6. So that goes away. So delta x is 2 times 6, 12 d. So if we look at it, so that's how we actually solve it out. But from our 1/2 k delta x squared, if we double this distance, we end up getting a factor of 4 increase in our potential energy from when it was just d. So if we look at the distance that we traveled, we started off a distance of 3d, and now we're a factor of 4 bigger for 12d. So there's two ways that you could answer this question. You can either go through and be like, okay, potential energy at the beginning, like we did with the 1/2 kd squared, mu mg 3d, and do all the math like we just did. Or you could also make the very reasonable argument of, well, from our potential energy, doubling the distance quadruples the potential energy. Therefore, it's going to quadruple the distance afterwards. Does that make sense? Okay. So we want to explain, cool. So we want to explain how the correct aspects of the student's reasoning identified in part B are expressed by our mathematical relationship that we found in part C. Explain how your relationships in part C correct any incorrect aspects of the student's reasoning identified in part B. Refer to the relationships that you wrote in part C, not just the final answer you obtained by manipulating those relationships. Okay, so this is when you would write a paragraph saying that uh, the student's correct reasoning that the block has more energy in the second situation is expressed in the calculations because we used that to show that the potential energy of the spring was 4 times as big by doubling the distance. We also showed that the student's correct reasoning that the block will slide farther was correct because we showed that in the second situation, the block goes 4 times further. Okay. And then we also indicated that the student's incorrect reasoning that the energy scales linearly with the spring's compression is corrected by our expression for the initial energy of the spring. Cool, cool. So part D is just writing a nice long paragraph. All right, so that is the only work energy example I was able to find in all of the past exams since it's been Physics 1. So do we have another topic that we want to cover? Let's go back to the point. So things that are ready to go, we have some conservation of angular momentum, rotational motion, and a short circular motion problem if you want any of those. Otherwise, you can be like, hey, can we do this thing? And I'll try to find one really fast. Or you can be like, hey, how's my test gonna work? And I'll link you a thing. All right, disk colliding and the wheel. And then we can do circular motion afterwards. Okay. Let's just go in order then, I guess. Cool. Since we have everybody wanting the things. Okay. All right. Totally lost on circular motion. Okay, cool. We'll make sure that we definitely get time to do that then. All right. So the first problem, we have the left end of a rod of length D and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot, as shown above. Point C marks the center midpoint of the rod. The rod is initially motionless, but is free to rotate around the pivot. A student will slide a disk of mass m disk toward the rod with velocity v0, perpendicular to the rod, and the disk will stick to the rod a distance x away from the pivot. The student wants the rod disk system to end up with as much angular speed as possible. Okay. So suppose that the rod is much more massive than the disk. To give the rod as much angular speed as possible, should the student make the disk hit the rod to the left of point C, at point C, or to the right of point C? And why? What do y'all think? To the right? To the right? Why? Remember that a lot of your free response questions, you're going to have to explain why you chose that. Right. Exactly. So you want to go to the right. So when we're talking about angular momentum and torque, so our pivot is the part that we're going to be rotating around, right? So remember that your torque and your angular momentum depends on how far away you are, right? So if your disk is hitting the rod, it is causing a torque on that rod. And that torque depends on how far away from the pivot you hit it, how far away the force is enacted. So the further to the right you go, the longer your lever arm and the more torque you're going to give to that rod. Exactly. Okay. Questions on that? While I take a sip of Coke. All right. Okay, so here's an example of the scoring breakdown for that. So you would get 1 point for just checking the right box, but then you also get points for explaining why. So don't forget to like write nice complete sentences for all of the things. Okay, and these slides are going to be posted on the website afterwards too. So we're just going to zoom through so that we can get to all of the questions. Okay, so B, on the internet, the student finds the following equation for the post-collision angular speed omega of the rod in this situation, where omega equals m disk x v0 over I. Regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning from part A? In other words, does this equation for omega have the expected dependence as reasoned in part A? Yay or nay? Yes. Why? How can you tell? How did you know that? X means a larger torque and velocity, right? Okay. So if we plug that in, so our omega depends on X linearly. So if X gets bigger, okay. So here's the part that you really want to focus on, right? So it says that does it agree with your qualitative reasoning in part A? So part A asks explicitly about where on the rod you're going to have to hit it, right? So when we're talking about the mass, the velocity, the moment of inertia, that's not in part A at all. So while yes, those things could be true, that's not what the question is really asking. So it wants to know based on X, how far along the rod you hit it, does this equation match what you said in A? So in this case, it would be yes, because as X gets bigger, omega gets bigger, which is what we expect. It spins faster the further away we hit it because we hit it harder. Cool? Okay. So for a selection consistent with your selection from part A. So this is another example that's really nice. If you get one of the parts wrong, they're not going to knock you off again. So as long as your answers are consistent with each other, you're only going to lose points for a mistake once. Thank you. No propagation of error. It's the best. All right, so as long as it's consistent with part A, and then indicating that the equation shows that omega increases with increasing X. So because part A asks explicitly about where should it hit, you want to make sure to talk about where it hits. You won't if you give extra info, but if you give the info and forget about X, yeah. So in this case, they're explicitly looking for you to talk about where, like talk about the X. So if you say like X increases, omega increases, and also MV whatever increases, that's great. But if you just say, well, MV increases and don't talk about X at all, then yeah, you'll lose points. Or you won't gain points, I guess. Cool, cool. So make sure that you understand what the question is asking because they're very picky. Okay. Also, writing complete sentences because they really like that. Okay. So part C. Another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with omega equals Ix v naught over m disk d to the fourth. Without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. So now, no, this is where you can start talking about, yeah, right? So as your moment of inertia increases, omega should decrease because remember, moment of inertia is like how much oomph it takes to get rotating. So the higher that is, the harder it is to spin. So the slower it should go. As m of the disk increases, right? The bigger the thing that hits it, the bigger the force, the bigger the torque, the faster the omega, right? So that should be on the numerator. M should be up top and I should be on the bottom to be consistent with that, right? So both of those are valid answers. So because they're not explicitly asking about a certain quantity, either of those would be. You don't have to say both, but as long as you say at least one of them, it's good. So like on here, focusing on the functional dependence instead of the unit analysis. So you also could have said that the units don't work out, but that's not really what they're looking for here, unfortunately. So in this case, for addressing the mass of the disk, the inertia, or both. So you would get points for either or both. Okay. And then being like, wait a minute, that doesn't make any sense. Cool. All right. So the nice thing about these is that a lot of them are like qualitative understanding or just like analyzing the situation. So you can get a lot of points on these questions without actually understanding the physics behind it, which is really nice. Why will the M have to be larger? Okay, so you remember in part A, let me go back to the picture. Yeah, so remember here, we were saying, okay, well, we have to hit it to the right because it'll make the longer lever arm and it'll make it go faster, right? So if you have a heavier disc hit it as well at the same speed, right? That thing's carrying more momentum, so it's crashing into it with more oomph. It's transferring more momentum to the rod. So if you have a larger disc crashing into it, it's going to be cause that rod to rotate faster. It's going to give it more energy. It's going to transfer more momentum, so it's going to spin faster. Oomph. Yeah, that's how I describe it. It's just easier to. I'm just like I like momentum's not a tangible thing, right? So I'm just like it's the oomph. It's like the oomphiness of it. That's how and like rotational inertia too. It's like you know how heavy stuff is hard to push? Like high inertia stuff is hard to turn. Okay, where are we? D. All right. Okay, so for parts D and E, we are not assuming that the rod is much more massive than the disk. So immediately before colliding with the rod, the disk's rotational inertia about the pivot is m disk x squared, and its angular momentum with respect to the pivot is m disk v naught x. Derive an equation for the post-collision angular speed omega of the rod, and express your answer in terms of the m disk I x v naught and physical constants as appropriate. Whoa, no, computer, I do not want to do updates right now. Okay, whew. Crisis averted. Alrighty, where'd my whiteboard go? There's my whiteboard. Da-na-na-na-na. Okay, do we have the question in our brains? Let's go over to the whiteboard. Also, I apologize in advance. Streams with me are full of singing and figuring out how to switch the stupid screens. Oh, shoot, wrong one. Does the disc stick to the rod? That's a great question. Let me go and look at the question one more time after I finish clicking all these buttons. Okay. Does the disc stick to the rod? Derive an equation for the post-collision angular speed of the rod. I think it did. To the left end of a rod from length D, notational inertia I is attached to a frictionless point C marks the center. Rod is initially motionless, is free to rotate around the pivot. Yes, the disc will stick to the rod a distance x away from the pivot. Okay. Okay. Whiteboard. Blah, 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 blah. New one. Okay. Okay. So in our handy dandy system, we have our rod and it's pinned right here. And then we have our little blob and it's coming in like, woo, blam, right here, a distance x away. Okay. So this is a collision, which tells us that this is a conservation of momentum. But because we are pinned and therefore spinning, it is a conservation of angular momentum. Coam. Okay. So the way I like to do these, I like to be like before, blam, after, blam. Okay, so before, I have my angular momentum of my disk, and I have my angular momentum of my rod, And my angular momentum of my disk was m. Hang on, what did they say? The moment of it. They gave you the moment of inertia, right? All right. So let's remember that L equals I omega. And they told us that I of our disk was m disk. V not. Wait, what did they give us? Hang on, I'm sorry. Back. The disk's rotational inertia about the pivot is m disk x squared. Cool. Okay, so m disk x squared. So that's I omega of my disk. Plus my rod, which was I rod and omega rod. But alas, my rod starts at rest, right? So, that's equal to 0. Okay. Now we also need to remember the relationship between omega and V, right? So, what was it? Was it omega equals V over R? Cool. I can never remember if it's V equals omega over R or omega equals V over R. But luckily, they'll give you an equation sheet, which is great. All right, so, dang it, I ran out of room. M disk x squared V over, and we're crashing in our at a distance x away. So our R is going to be x. Okay, you know what? I'm just going to write this over here. Blah, 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 blah. Okay. So M disk x squared V over R. But R is where I'm hitting the rod, which is the same thing as x, which means this cancels this. So my L before is md x v naught. Sorry, just so that we're consistent. Okay, so this is before. Before. We good on that part? We good on before? Cool. So the rod is this part right here. Let me box it for you. Box. Bing, 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 bing. So the rod, because it starts at rest, its angular momentum at the beginning is equal to 0. So everything that we're writing right now is before the collision, like right when it's here, just about to hit. So we have the angular momentum of our disk plus the angular momentum of our rod, because those are the two things in our system, right? So our disk, this is I omega, but omega for our rod, it starts at rest, so that's equal to 0. So that's why that goes away. And then omega, we wrote in terms of V over R. And R in this case is where it hits the rod, which is X, which is why one of those canceled out. So this is our angular momentum before, right before. And it's only the disk because the rod starts at rest. Cuckoo. All right. So let's go to after and see what happens. Okay, so then after, we have L disk plus L rod. All right, so now I have my disk, which is I, so m disk x squared, omega. So this time it's stuck to the rod, so I'm just going to go ahead and leave it as omega instead of v over r. Because now it's stuck to the rod, which means they have the same angular speed because it's stuck. So it's now like spinning in a circle. Okay, so if I pull that out, I get m disk x squared plus I. Okay, so now for our conservation of angular momentum, whatever we start with is equal to whatever we end with. Bum, 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 bum. So now we can set those two things equal to each other. So m disk x v naught is equal to omega m disk x squared plus I, and solving for omega, so we can just divide all this stuff over. So m disk x v naught over m disk x squared plus I. Beep, 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 beep. Hey. Cool, cool. All right. I'm going to switch back over if we're ready. Ba-ba-bum. Okay. Okay. Thank you. Big. So we only use the momentum that was given in the question. Yep. Yep, yep. So everything that they gave us is what we have. What was I trying to say? Yeah, so because they told us the disk's rotational inertia, and we know that oh look, they even told us the angular momentum, so we could have just used that instead of saying I omega, but it's the same thing. Yeah, so all we did was use conservation of angular momentum in this question. And so because they give us the angular momentum of the disk, and our angular momentum of our rod starts at 0 because it starts at rest, then we can say angular momentum at the start is equal to angular momentum at the end. So point breakdown for that one. Just saying that you're using conservation of angular momentum is equal to 1 point. But you have to be careful that you're using angular momentum, not linear momentum, because your rod is rotating. So it's angular momentum because it's pinned at that one end. All right. Our initial angular momentum of the system is just of the disk because our rod is at rest. So that gives you a point. And making sure that your dimensions, dimensionally correct expression for post-collision angular momentum that includes I omega. Yeah. So including that the rod is now moving, so we have that extra factor of I omega. And then the system afterwards is the rod plus the disk. So we got all those things. All right, so then part E, consider the collision for which your equation is in part D was derived. Except now suppose the disk bounces backward off the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disk bounces off greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks to it? Explain your reasoning. What do y'all think? Drink break. If instead, Yep, exactly. So before, when your disk came in and hit it, boom, and it kept traveling forward with the rod, that momentum that you start with is now still going in the same direction. It's just going to be going slower because it transferred some to the rod. But now, if your disc comes in and goes boink boink, now you have to not only transfer the forward momentum to the rod, but the backwards momentum gives it that extra boost. If that made any sense at all. Yeah. So your elastic collisions are always going to transfer more momentum. Because instead of just canceling out the forward motion, now you have to cancel out the forward and backward bounce. So like if you go a little bit this way, you got to cancel it out with a little bit this way. So if your thingy is going this way, then you get more this way, and then it bounces back. Now you have to add an extra factor of this way. I'm just making words now. Does that make sense? Do I need to draw things? I will draw things. Let me know if you want me to draw things, because I will. Okay. I'm going to take that as a we're good. All right. Yeah, so it's greater than, because you have to balance out the disk going back. So your angular momentum transfer is greater. All right. Where did my thing go? Okay. All right, so you get 1 point for correctly indicating greater than. All right, so the disk angular momentum with respect to the pivot changes more in the bouncy scenario than in the original scenario, or using a similar argument in terms of impulse. So because you're not sticking, now your contact time is a lot smaller, so your force is bigger. So you're pushing it more. Yeah. All right. Okay. Okay, so now we're going to the rotating disk question. Don't worry, we'll stay here as long as y'all want, okay? We said we wanted to do the disk, so we will do the disk. And we said we wanted to do circular motion, so we will do circular motion. Okay. This problem, we have a disk shown above spinning about the axle at its center. A student's experiment revealed that while the disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. So this is a question that's not super clear, but the axle is not attached to the disk. So it's just a disk with a hole in it, and then the axle is in the middle of it, but that axle can still rotate inside. So it's just friction between the two that's causing the disk to rotate. And like you kind of pick that up in the context of the problem, but from this right here, that's not super clear to me. Okay. Okay, so part A, at time t equals 0, the disk has an initial counterclockwise positive angular velocity omega naught. The disk later comes to rest at time t equals t1. On the grid left below, sketch a graph that could represent the disk's angular velocity as a function of time from t equals 0 until the disk comes to rest at time t equals t1. And on the right side, sketch the angular acceleration as a function of time. So, what is our angular velocity graph going to look like? Is it going to be constant? Is it going to be linear? Is it going to be quadratic? Is it going to be some piecewise function? What's that going to look like? It's going to be linear. Good. Here's the situation again. FYI. You have the disk with the rod spinning, and it's friction causing a torque on the disk. So our disk starts with a positive angular velocity, and then it comes to rest later. It's going to be nice and linear. So we start off at t equals 0 at our initial velocity of omega naught. And then we come to rest, so it's a better end at 0 over at t1. And then because it's friction that's messing with this, remember friction is a linear function when we talk about the work. So that's going to be a nice straight line. And if you have a constant angular or a linear angular velocity, dang it, I just gave it away. What's the acceleration going to look like? Constant, but in the negatives, exactly. So you're slowing down, so it's going to be negative. And it's a linear decrease in your velocity, so it's going to be a constant acceleration. Good. Okay. So point breakdown for starting at omega naught at t equals 0 and going to 0 at t equals t1. So the two things that they give you in the problem, if you include those on your graph, you get half the points. Good job. And actually, no, you get all the points. Oh, no, yeah, you get half the points. No, excuse me. And then having a straight line with a negative slope showing that the angular velocity approaching 0. Yeah, see, it's weird because they say for a curve that is a straight line. So curve is just like the general term for a line on a graph. Um, yeah, that's it. So curve is just like the general term for a line on a graph, and then it specifically says that that curve is a straight line with a negative slope showing the angular velocity approaching 0. Okay, and then for 2, your curve needs to be negative the entire time because you're slowing down. And your curve needs to be a constant non-zero function. So it needs to be straight. Yeah, so curve is just the line that you draw. That's all. Okay. Part B, the magnitude of the frictional torque exerted on the disk is tau naught. Derive an equation for the rotational inertia I of the disk in terms of tau naught, omega naught, T1, and physical constants as appropriate. Okie dokie. All right. To the whiteboard we go, we're going to the whiteboard. I love the whiteboard. Okay. All right. What do we got? New tab. Blank. Okay. So what do we know? We know that our disk starts at some initial velocity at time t equals 0. We also know that it goes to 0 at time t equals t1. Cool, cool. And we want an expression for the torque. What was it? Oh no, we want an expression for the inertia. Okay. So we know from the rotationally version of Newton's second law that the sum of the torques is equal to I alpha, right? So in this case, the only torque acting on our disk is tau naught. It's equal to I alpha. So we need to get the angular acceleration from the things that we know, right? So we know angular acceleration is the change in angular velocity over time, right? So omega final, 0, minus omega initial, over T final, which is T1, minus T initial, which is 0. So alpha is minus omega naught over T1. So negative because we're slowing down, omega naught over T1. Okay? So if we come over here, we have tau naught equals I minus alpha is omega naught over T1. So if I solve for I, it's going to be tau naught times T1 over omega naught. Oh, and with my minus sign. Okay. Alrighty. So now you could do this with or without the minus sign. Because your rotational inertia can't be negative. If you have the minus sign in here, that just means that it's going to be canceled out either by the direction of the torque or by the direction of omega naught to give you a positive answer. But either one of those is going to be accepted, either plus or minus. Okay. And then we switch back. And okay. Focus screen. Wow. All right. So here's the scoring breakdown for that. You get 1 point for using the rotational version of Newton's second law. So it's sum of the torques equals I alpha. Kinematic equation, the alpha equals change in omega over change in t is 1 point. The correct answer is 1 point, with or without the minus sign. You also could have done it using conservation of angular momentum and rotational impulse. Well, not conservation, angular momentum and impulse from change in L equals tau delta t. So remember, angular momentum is I omega and tau delta t. So that's how they get it from there. Okay. Blam. Okay, so in another experiment, the disk again has an initial positive angular velocity omega naught at time t equals 0. At time t equals 1/2 t1, the student starts dripping oil on the contact surface between the axle and the disk to reduce the friction. As time passes, more and more oil reaches that contact surface, reducing the friction even further. On the grids, sketch your omega t graph and sketch your alpha t graph. Okay, so everything is the same up until 1/2 t1. So our velocity is going to stay the same and our acceleration is going to stay the same. So what are you changing when you drop the oil onto the axle? Like, what is that oil doing? It's reducing the torque, right? It's reducing the friction, and the friction is the thing causing the torque. So if you're reducing the torque, you're also therefore reducing the angular acceleration. So our angular acceleration is going to start getting closer to 0. It's getting less and less and less. So if our acceleration is getting smaller or less negative, what happens to our velocity? Flattens out a bit, exactly. So it starts coming and flattening out. Yep. If it does want to come down rather. For the acceleration, is that what you mean? Yeah. So because it starts off negative, the magnitude is greater. So like if we look at it, it starts off with a magnitude of 2 blocks down. So when we talk about getting less, we're talking about the magnitude. So it's getting closer to 0. So now it's only 1 block down if we get it smaller. So it's negative because it's slowing it down. So it starts off slowing it down a lot, and then it's slowing it down less and less and less and less, which is why it comes closer to 0. So if it was a positive acceleration, it would come down, but because it starts off negative, it gets closer to 0. Does that make sense? Does that answer your question? No. Okay. Uh so you agree that the acceleration decreases. Yes or no? Like just that statement. The part that if you're oiling it up, you're reducing the torque, you're reducing the friction. So you're reducing the torque, so you're reducing the acceleration. Does that part make sense? Or is that part clear? Is it just the graph? Yeah, okay. Yeah, okay. So we're oiling the axle, so we're reducing friction. We're reducing friction, we're reducing torque. And if we reduce torque, we reduce acceleration. So if we, let me switch back over to the whiteboard, blah, blah, blah. So if our torque was responsible for speeding something up, right? So if we were looking at our acceleration time graph, the acceleration, okay, so what's going on? We start off by spinning the thing around, and then we let go, and then we just let it spin and stop on its own, right? So because there's that friction inside, that friction is going to cause that disk to slowly stop spinning, right? So the acceleration, it's a deceleration. It's slowing the disk down, right? So if I'm throwing more oil in here, that disk is going to be spinning a lot longer. That acceleration, that deceleration is not as strong. So because it's a deceleration is why we start off down here underneath 0. Because our disk is spinning and then it slows and it's just left to slow down because of friction. So it's a deceleration, which is why it's down here. As we add oil, we're making it slipperier so that disk can keep spinning a lot longer before it comes to rest. So that friction is doing a lot less to slow it down. So it's still slowing down, just not as fast, which is why it's closer to 0. And so that's why we drew it like that. So if, say, we were, I think what might be happening, so if we were starting at rest and then we were spinning the disk and had a positive acceleration and then we added oil, it would be slipperier, so then it would go like that. I think that might be what you're picturing. Yeah, okay. Yeah, so the red is if we start at rest and then spin it and go. Then it would be a positive acceleration, and then oiling it would make it slipperier, so it would go down. But that's not what the problem is asking. The problem is asking is if we already spin it and then we just let go and let it come to rest later. So it's slowing down because of friction, and then it's slowing down slower as we oil it. So then it comes to rest. Goes down here. Okay, cool. Cool. On the same page now. Let's go back to the thing. Thanks for sticking around, guys. Y'all. Thanks for sticking around, y'all. Okay. Okay. Right, so that's where we get our points for keeping the graph the same for the first half and then showing a decrease in the speed afterwards. And it does not reach 0 before time t1 because it's going to take longer to slow down. And then for our acceleration, it doesn't matter just as long as it gets closer to 0. Okay, so now the student is trying to mathematically model the magnitude tau of the torque exerted by the axle on the disk when the oil is present at times t greater than 1/2 t1. The student writes down the following two equations, each of which includes a positive constant, C1 or C2, with appropriate units. Which equation better mathematically models this experiment, and why? What do y'all think? And I think this is the last part, and then we can hop into that nice circle parabola. All right, which equation is better, 1 or 2? No idea. Okay, so probably the quickest, bestest way, most straightforward way is to look at your inflection points, right? So I know that at t equals 1/2 t1, something funky is going on. So let me plug in 1/2 t1 and see what happens. So for equation 1, if I plug in 1/2 t1, my torque is equal to 0. Is my torque ever equal to 0 in this case? Anywhere between t equals 0 and t equals t1? No, exactly. So that doesn't track with what we drew on our things or what we talked about on our things. Because remember, torque is related to your acceleration. Whereas in equation 2, if I plug in 1/2 t1, my torque is a constant over t1, which is still a value. So that acceleration, that torque still exists, which we know it does because friction is slowing down our disk. We drew that in the last two parts, right? Our acceleration was never equal to 0. So the fact that equation 1 gives me a torque of 0 and right in the middle means that it's not great. It's not a good expression. So when you get questions like this, that's like, what's the best one? You want to look at your inflection points. So where do I know things are happening? At t equals 0, t equals 1/2 t1, and t equals p1. And just make sure that the result of those equations is consistent with what you know is going on. Another argument that you could use is dimensional analysis. Sometimes that works. In this case, because it's just constants and t's. As time increases, torque increases. Decreases. Yeah. Yep. Because like as you get greater than t1, remember we're oiling it up. We're decreasing our friction, so we're decreasing our torque. So our torque should decrease as time goes on. Yep. Exactly. Okay. But it should still be consistent. So the dead giveaway for this one was that t equals 1/2 t1, torque was 0, and torque is never 0 in our thing. And then again, our torque needs to decrease as time gets bigger, which it does in equation 1, but or decreases. Well, if the constant is negative. Anyway. Okay. So, how they explain that? Equation 2. This is one where if you check the wrong box, your explanation doesn't count for anything, which kind of stinks, but it's only 1 point. Will we meet before the test? Yeah, so there's a big stream next week. I don't remember if it's at 1 or at 7, but there's like a mega Q&A stream next week on Wednesday. 4 to 9, perfect, thank you. So I wasn't right at all. So from 4 to 9 Eastern Standard Time, and I think Peter is leading that one, so he'll have lots and lots and lots of things prepped. Yeah, because he's a super preppy guy, and he's been doing this a long time. Is it Krampus? I don't think so. I don't think so. I think everything that's live, if you attend live, you can go to any of them. But if you want to look at them later, it's Krampus. Really? Dang it. Okay, I'm just answering all your questions wrong. I'm so sorry. It's not my stream, so I don't know. Thanks, Nell. Okay. But in the meantime, I'll hang out here if you have any more questions. For free. Okay. Now, as promised, we're finally getting to our rotational problem. Okay, so this is a shorty short free response question. So it's not a good indicator of what they're going to look like on your fake internet test, or I guess not fake, your short internet test. But it's still good practice. So we have a spacecraft of mass little m is in a clockwise circular orbit of radius r around Earth, as shown in the figure above. Mass of the Earth is capital M-E. We have a little spacecraft. Boop-a-doop-a-doop. In the figure below, draw and label the forces, not components, that act on the spacecraft. Each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. So what forces do we have? Gravity! Are there any other forces? No! Good. Which way does gravity point? Towards the Earth. Exactly. To the middle. Yep. So, blam, that's our free body diagram. The only force that exists is our force from gravity. It is the thing causing the orbit, so it is pointing to the middle of the circle. Cool, cool. So I think one thing that causes a lot of confusion with circular motion is there's this, isn't there this, that would be tricky. What's this, this STH, what's that? Something. If it said something like, yeah, so if it said something like the rocket is thrusting and accelerating, sure, but in this case, because it's just the satellite in orbit minding its own business, the only thing acting on it is gravity. And remember that your centripetal force is not a force. It, like, in its own right. It's not a separate force. It's the force causing you to be in a circle that is the centripetal force. So in this case, gravity is what's causing us to be in a circle. So gravity is the centripetal force. Because I know that's like a big hang up with circular motion is like people are like, oh, it's moving in a circle. There has to be that force pointing to the middle of the circle. Well, yes, but it's gravity. It's not a separate force. Okay. All right, so now we want to derive an equation for the orbital period t of the spacecraft in terms of little m, big M, r, and physical constants as appropriate. If you need to draw anything other than what you have shown in part A, Use the space below. Don't add anything to part A because you'll lose points for part A. All right. We're going to hop over to the whiteboard super fast. Hello from my face up close. Blam. And share. Blam. New thing. Okay. Okay. So we are moving in a circle. That tells me what? That tells me that my acceleration is v squared over r. Right? I also know Newton's second law, F equals ma. So that tells me that the sum of my forces is equal to m v squared over r. My force is my force from gravity. And my force from gravity is big G, little m, big M, GMM over r squared. I'm just going to put this back on the end so that it doesn't get lost. Okay? So one of my r's cancels out. My little m cancels out. QQ. So now I have big G, big M over r is equal to v squared. Okay. We're just going to put that aside. Put it in the box for later. And what are we trying to find again? The period? All right. So we know that the period, capital T, is the amount of time it takes to go one orbit, right? So my distance is 2 pi r because I'm traveling in a circle. So my distance over time is equal to velocity. But over here, we said that velocity squared was gm over r, right? So using those two things, my distance over time is equal to the velocity that I get from my sum of my forces. So my period is equal to 2 pi r over the square root of g m over r. We can make that look prettier. By putting the 2 pi r inside, so square everything, so it's 4 pi squared r squared over g m over r. So r squared r is r cubed. Cool. And that is your orbital period. So the important thing to notice here is that the mass of my satellite canceled out in my force equation, because that becomes relevant come GMM over r squared. Okay, yeah, so that is the generic form of, okay, yeah. Let me go back. Okay. So, first question. GMM over r squared, that is the generic form of force of gravity. So big G MM over r squared. This, yeah, it's on the equation sheet, yep. So this for Earth is little g. That's 9.8 meters per second squared. So once you get far away from the surface of Earth, your force of gravity starts becoming distance dependent. But at the surface of Earth, it's approximately. We did not compare them both, no. So because we're a satellite in space, okay, hang on. Let's roll back. Right. So because we are a satellite in space, the force from gravity from our free body diagram here is GMM over r squared, where r is the distance from the center of the Earth to my satellite. Cool, cool. So that's where that comes from. Uh, if somehow you were magically able to like hoverboard right above the surface of the Earth and then like fly around it, you could use 9.8 like mg, like we always do. But because we are far away from the surface of Earth, we're a satellite, we have to use the full version of force of gravity. So that's where that came from. So then we set it equal to mv squared over r. That is not an r, because this force is what is causing the circular motion. Cool? So whenever we're looking at circular motion, we know that our centripetal force is mv squared over r. But that is caused by, big equal sign, my force from gravity. So that's why we set them equal to each other. Does that make sense? Cool. So from there is how we canceled these things out. Yeah, exactly. So it starts from F equals ma, and then a is v squared over r. That's also the other way you can look at it, which is what we did the first time. Yeah. Okay. So then from my distance over time, 2 pi r over t is equal to v, right? So from here, v squared is equal to gm over r. So I'm going to square this so that I can set those two things equal to each other. So 4 pi squared r squared over t squared. So v squared equals v squared. V squared from here, v squared from there. Cool, cool. So now if I move my t's to the other side, so I get t squared equals 4 pi r. Take this r, move it over here, so that's an r cubed, over gm. And now, if I square root it all, blank. That's the period. Yes? Questions? Are we good? Anything still not clear? We good. D over T. Cool. Okay, so we good from now? We good, Carol? Is it? No, it's the same. It's the same answer. It's just a different order of steps this time, or a more clearly laying out the algebra magic. It's the same answer. Should be the same answer. Yeah. Back to the thing. Okay. All right. So, a second spacecraft of mass 2m is placed in a circular orbit with the same radius r. Is the orbital period of the second spacecraft greater than, less than, or equal to the orbital period of the first spacecraft? What do y'all say? Okay, but which m? Which m is in the denominator? Big M or little m? Yeah. Yeah, so remember from our equation that we just got, it was 4 pi r cubed, so it depends how far away you are, over g big M. So it depends on the mass of the planet, not the mass of the satellite. So they are going to have the same orbital period. It's it's very similar to, like, the pendulums, how the mass of the bob on the pendulum doesn't matter for the period, just the length of the string. It's the same here. So the mass of the thingy orbiting doesn't matter, just the distance. So they have the same orbital period. Uh, oh, I don't remember what year this is from. I can go pull it up really fast though. Here, I'll go pull it up really fast while you guys take a look at part C. I mean, I have it open. I just have to go look at it. Just have to go remember where it's from. I know it's problem number 1 on 2018 is where it's from. Problem number 1 on 2018. All right. Okay, so now our first spacecraft is moved to a new circular orbit that has a radius greater than r, as shown in figure below. Is the speed of the aircraft in the new orbit greater than, less than, or equal to the original speed? So now this is why it's very nice to write down all of your steps. Because, looky here, when we already looked at what does our speed depend on? So, this one's tricky though. So if you look at the speed is 2 pi r over t, t depends on radius too. So radius is not going to be the same. So the safer bet is to look over here because g is not changing, m's not changing, but r is. So if r gets bigger, right, v gets less than. So I mean, like, we could like go in there and be like, okay, if r gets bigger, t gets bigger, but then hang on, can we do this? Okay, so y less than. So when we go back and we look at our handy dandy things, we have two expressions of v that we came out of, right? we had our v squared was gm over r, and we had our v squared was 2 pi r over t all squared, right? So this is where it can trick you. Because if we look at this one, we're like, okay, r is in the numerator. If r gets bigger, v gets bigger. But the period also depends on r. So that's gonna trip you up. Whereas over here, my expression for v, that is the same as this one. Because remember, we set them equal to each other. G is not changing. That's a constant. M, the mass of my planet's not changing. But R down here is the only thing that's changing. So as R gets bigger, V gets smaller because it's in the denominator. Cool, cool. Okay. That is not where my mouse lives. Okay. Okay. Let's go. I think that was the end. I think that's the end. It ran really long today. Sorry, guys, but I wanted to make sure that we got through all of the things because everybody said they wanted to do the things. So thanks for sticking around. Okay, yeah, so the correct answer is less than. Yeah, for what we just explained. Wow, okay. So you can use your answer from part B to be like, speed decreases because R is in the denominator. But so when you're doing things like that, make sure that other things in your equation aren't also dependent on the thing that's changing. So like we almost fell into using the 2 pi r over t. Remember, the period depends on how far away you are. So that had a double dependence there that kind of screwed things up. Okay. Yeah, for sure. Okay, that is the end. Here is my email. Wham. Cool. Yeah, so that's my email if you guys have any questions. There's the mega stream next week, which is apparently 4 to 9, run by Peter. And it costs $5, which I didn't know. Yeah, so check that out. Peter's great. He does a very, very, very good job at answering questions. He's a very good prepper. And if you have any questions, email me. I'll be around. Good luck. Oh, if the button didn't show up, that's not it. There is a super neat video that explains how your AP exam is going to work. If you haven't seen it, I'm going to post it in the chat right now. Copy link so that you can watch it. And I think it does a really nice job of explaining how your test is going to work. So good luck. I wish you all the best. If I don't see you before then, I hope you all get 5s. And I hope I see you next year for Physics C. Because I'm trying to get them to do Physics C. Yeah. Or I guess you might be in college. I don't know. What are y'all doing? Cool. So good luck. Have a good night. Thanks for sticking around an extra 45 minutes, but I wanted to make sure that we answered all your questions. Well, the requested questions. Yeah. Thanks, guys. Thanks, y'all. Have a lovely evening. Farewell.